Yeah, it's visible.
All right. So what are we going to do today is, oh my God, this is so, pen width is so much. All right. So what are we going to do today is, we will learn about zeroth law of thermodynamics.
I learned about that.
Yes.
Yeah,
So
it's
yes. So
like
if you,
when two, I don't remember if it said systems, but I think if like it said if two systems are in thermal equilibrium with a third system or something. Right, I have it written down in my physics workbook for class.
okay. So well said. You have given the bang on right answer, Swapnil. Yes.
Mm-hmm.
Two systems in thermal equilibrium with the third system separately in thermal equilibrium, then they
Yeah,
are said to be in equilibrium with each other. So what do you
yeah,
mean by that? See, suppose if there are two systems, say A and B, they both are in equilibrium,
there it is.
right?
Yeah. Mm-hmm.
Or if I say like this, okay, so A is in equilibrium with C and B is also in equilibrium with C, that implies that system A and B are in equilibrium. So what am I trying to say? A system is in equilibrium with B and another is also is in equilibrium with C. That implies that A is in equilibrium with B. That is what we are trying to say. Superb. It is called the zeroth law of thermodynamics.
Yeah.
Okay. Can you tell me who invented this zeroth law of thermodynamics?
Oh, we didn't learn about that.
Okay. So that is none other than Mr. Cobbler in the year 1931. All right.
Yeah.
So just for the information, like 1 mark questions or answers, if you get, you should do
Yeah.
that.
Okay.
Okay. So basically, it says that, I mean, the significance of this zeroth law of thermodynamics is that it should be in physical quantity, which should have the same value when two systems are in equilibrium. And when
Mm-hmm.
I am saying this physical quantity, what am I talking about? The physical quantity which I am talking about is nothing but temperature.
Mm-hmm.
Correct? So
Yeah.
I can say temperature is the quantity which determines whether or not the system is in thermal equilibrium with the neighboring systems, right?
Mm-hmm. Yeah.
And why we say that it is, I mean, it is so significant, why the temperature plays the main role, because it gives birth to the signs of, or the signature or the significance of temperature. All right.
Mm-hmm.
And that is why we are saying physical quantity.
Mm-hmm. Yeah.
Correct. And this is, do you know why it is called zeroth law? Why do we call it zeroth law? Why not third law, fourth law, fifth law? Why zeroth law?
I'm not sure.
Because it was invented after first and second law. Correct. Now, first and second law was already defined. So what
Mm-hmm.
happened? You had to predict, you have to create a law which is before that. I mean, this is something which we tell first. So
Yeah.
we gave the name before first, that is zeroth. So that's the reason it is also called that zeroth law of thermodynamics.
Okay.
Okay. And here the basic thing, the main important thing, the temperature as in physical quantity was known, or the significance of that was known. Okay. Now, you remember we learned about few state variables. What were those? I'm just revising it once again with you. Pressure, temperature,
Temperature,
volume,
and
mass,
yes,
and internal
energy.
energy. Excuse me for the spelling. Okay. Right? So what I said, it is of two types. One was extensive and one was intensive. So in extensive, what all comes?
Extensive is
Pressure comes in
um,
extensive or intensive? Quickly.
extensive.
No. Pressure is in intensive. Okay. Temperature?
Temperature is extensive. No, temperature is intensive
See,
as well.
intensive means which does not depend on the size. Does it depend on the size? Pressure is dependent on size? No.
No.
Temperature? No. So that's why intensive. And rest all are mass. Mass is what? Mass is what? Number of particles.
Yeah.
It relates to what? Size.
Yeah.
That's why extensive. Right?
Yeah.
Volume. Again, it is a quantity. Right?
Yeah.
Volume again extensive. Internal energy extensive. Right?
Yeah.
And we learned about the equation of the state, that was PV is equal to mu R and T. Remember?
Yeah. PV is equal to I think I remember.
Equation of a state, right?
Yeah.
Equation of a state as in equation connecting the state variables. These are what? These are what? These are all state variables. So what is this equation? This is connecting the state variables.
Yeah.
Yes?
Yeah.
So if you talk about P is what? Pressure.
Pressure.
P is
volume.
What is mu?
Is it? No.
Number of
moles.
molecules.
Oh, is it molecules?
Okay. And what is R?
R.
What is R? Universal gas constant.
Okay.
It is actually PV is like this. So this.
Does that mean proportional?
Yes. So these are, this is getting replaced with this R, the constant.
Okay.
Right?
Yeah.
So that means all state variables are not independent. They are dependent, right? Suppose if I write P is like this, so if you increase pressure, temperature will also increase, right? If you say decrease volume, the temperature will also decrease. So they are not independent, they are dependent, right?
Yeah.
Okay. So I think this was the last class discussion which we did, the internal energy and the equation of the state, just to bring you back. So now we will learn something new, which is called internal energy. Okay. So what do you think? What do you think is internal energy? Any definition, anything you can think of?
Internal energy. I'm not really sure.
Okay. So basically, Swapnil, when I'm talking about internal energy, it is actually the energy of the object as a whole. So what am I saying? Energy of an object as a whole. That means if there's an object, any object you can say a mobile. So as a whole, I will consider that system as a whole. It is what? It is an extensive quantity. Okay. That means, see, mass, value, it has some size. That is why it is what? It is an extensive quantity. One more question. Internal energy is dash. Or internal energy is an extensive quantity, true or false? So one more question. All right.
Yeah.
It is denoted by U. Okay, it looks like mu actually. So I will make it more clear. Oh, pen. Okay, it is denoted by U.
What does mu look like?
What?
What does mu look like?
Okay, this is not actually mu, this is U, energy.
Yeah.
Internal energy is represented by U. So it is just a representation.
Yeah.
Like
but,
apple A is called A, like that.
Yeah,
Okay.
but you said M was mu. So how do you represent mu?
Okay, this one you are talking about, this mu.
Yeah.
Right?
Is it just M? Do you just write M?
No,
as a symbol?
This is mu. You can write M for molecules.
Yeah.
See, this and internal energy are little different. You will come to know after you study first and second law. I'm coming to it. Okay. So currently you can just remember this equation. I will tell you where this internal energy will come into picture. Okay. After few more minutes. Okay. All right. Then it is the macroscopic variable of the system. What are macroscopic variable? Macroscopic variable. Anything you want to say?
Macroscopic.
I told you in the first class. Macroscopic means bulk systems. Bulk. Can you imagine? Huge. All right.
Yeah.
And what are the macroscopic units? Volume and temperature. These are what? Macroscopic. Okay. So basically, why am I saying all this is internal energy is basically sum of kinetic energy and potential energy of the molecules constituting the system. So if this is a system and there are many molecules, so they must be moving around. So they must be having some kinetic energy plus the potential energy of its own. Okay, so this is what I say is what? Equal to U, internal energy. Once again, internal energy is what? Sum of kinetic energy plus potential energy of the molecules constituting the system. Right? So if a question comes in the exam for internal energy, what all will you write? It is the sum of kinetic and potential energy of the molecules constituting the system. It is the energy of the object as a whole. It is an extensive quantity. It is denoted by U. It is the macroscopic variable of the system. Right?
Yeah.
Okay. Now your question. This energy is not visible. Why am I constantly saying ki no, this don't confuse with this? No. Why? Because this is something internal which is not visible. Because it is the energy of the system as a whole.
Yeah.
Okay.
Yeah.
Now, if I have to change the internal energy, then what will happen? You said, ma'am, you said that it is not visible. Now, if I have to change the internal energy, how will I come to know that there was an energy or there was a heat, and how will I come to know? So basically, Swapnir,
Mm-hmm.
here two principles work. That is heat and work. So these are two different modes of changing the internal energy of the system. So what do you mean? Heat and work constitutes what?
Internal energy.
Internal energy. So you will say, okay, can we have an example on this? Can you think of any example?
Um, for example.
Okay, I will tell you.
Yeah.
Apply the pressure on the bottle. What happens? When you are applying some pressure on the bottle, any bottle, what is happening? There is work done.
Mm-hmm. Yeah.
Correct?
Yeah.
Or if you have a balloon tied to a bottle and you heat it from the bottom, so that is what? Heat. Heat. Maybe what will happen? Maybe balloon will, it will move around, it will run away, or maybe it will blast. But
Wait, so when you heat the balloon from the bottom,
yes, tied on a, not the balloon directly, but a balloon tied to a bottle and which is heated from the down. Suppose you tie a balloon on the top of a bottle and then
mm-hmm.
you try to do it. So what happens? The bottle absorbs the heat energy, and through that heat, the balloon changes its state. Right?
Okay, yeah, when the balloon like increases in heat energy or like absorbs the heat energy from the bottle,
Yes.
then does it expand?
Yes. It may expand, it may blast, it depends.
Okay.
Right?
Yeah.
So basically, what am I trying to say over here is that heat and work, what are these? These are not state variables. So what are these? These are basically modes of transfer. What are we transferring? Transferring to a system resulting in the change in its internal energy. The internal energy of a balloon changes. So
Mm-hmm.
that is why it is said that these are the modes of transfer.
Wait, what do we change again?
Okay. What do we change again is we are changing the what?
The
Internal energy. U. We are talking about U.
Wait, but what do you mean by modes of transfer?
Okay. Modes of transfer is like, okay, tell me modes of transport.
Yeah,
So
you
if you have to
travel
go
somewhere.
from, say, London to maybe Australia or maybe to some nearby place, you will take some mode of transfer.
Yeah.
Transport, right? Maybe a car or by a plane or maybe through sea. So these are the different modes of transportation, right?
Uh-huh.
Same way, what is happening over here is when I gave you an example where you're applying a pressure on the bottle, what is happening? There is some energy. Do you think when you're holding something for a longer time, it becomes warm? Why? Because of the
Um,
heat which is there in your hand, it gets transferred to that material. Mostly
yep.
it happens in winters, right?
Yeah.
When you're holding something for a longer time. That's why when I said you are heating a bottle, so the balloon, maybe it might burst, maybe it might get inflated, you don't know. But there will be some transfer happening. There is some
Yeah.
change happening. So that's why we are saying that these are modes of transfer. Like from one system to another system, something will happen. But how this will happen? How will you travel from one place to another using the transportation vehicle? Same way, these are also like that. Heat and work modes of transfer.
Okay.
Transferring from here to here.
Wait, heat and work are modes of transfer. That's
Yes.
that's a transfer energy.
Okay. Let's do one simple example. I think the imagination is going a little wrong, but okay. What we do is we rub our hands, right?
Mm-hmm. Yeah.
What happens when you rub your hands?
They become warmer
They become warmer. Why?
because of the friction.
Because rub
Mhm.
your hand. Which energy? Mechanical energy. Mechanical matlab work done. You are doing some work,
Yeah, yeah,
right?
yeah.
And you only said, ma'am, it becomes warmer, right?
Yeah, yeah.
So that means mechanical energy, the work done, the work we did. What is the work we are doing? Rubbing our hands. So that's a mechanical energy. That's a work done, which is
Uh-huh.
getting transferred to or which is getting converted to heat energy. Your palms
Yeah,
become warm. So
yeah.
what are these? Mechanical energy is transferred to heat energy or mechanical energy is converted to heat energy.
Okay.
Okay.
Yeah.
And Swapniv, with this, you have also learned your first law of thermodynamics. Why? Because what I did, I said mechanical energy getting converted into heat energy.
Mm-hmm.
That means energy can neither be created nor destroyed. It can only be transferred. See, the word
Yeah.
came. Transferred from one system to another, right?
Uh-huh. Yeah.
And that is what our first law of thermodynamics states. So what is this? Energy can neither be created nor destroyed, right?
Okay. Yeah.
See, suppose, okay, can you give me one example of it? Example of this, like I gave you simple example of rubbing your hands. Then yes. Any other example? Yes, Swapniv, come on. First law of thermodynamics, energy can neither be created nor destroyed. It can only be transferred to other forms, right?
Yeah.
It can only be transferred or transformed, you can say, to other forms. So see, definition also I've written.
I have the first law of thermodynamics written in my book, and it says the total energy of a system can be changed by heating or cooling or by work done.
Yes, exactly. Even that
Um,
also applies. Correct.
yeah, yeah.
Both are saying the same thing only. Do you know what is this actually called? First law of thermodynamics. It is known as restatement principle. Why restatement principle? Because it talks about conservation of energy. Why energy is getting conserved? Because it is not getting destroyed. It is just getting transformed. Like I told you, rubbing of hands. Second example is ball falling from a wall. What happens? The ball is here, okay? So ball has some potential energy. When it is falling down like this, so what is happening? The potential energy is getting converted into kinetic energy. Something which was in no motion, like here it was stable. It has started rolling down. It has started coming down. So it has started moving. That means kinetic energy.
Yeah.
Right? So what is this? Potential energy getting converted into kinetic energy. This is what? This is transformed energy or transfer.
Yeah.
Right?
Yeah.
Yes?
Yes.
Yes. So even what you have written in the school also, that is also correct.
Okay.
Okay. Now,
Yeah.
Swapnev, your doubt will get cleared over here just now in another 2 minutes. Now, when I have to write this, I'm talking about potential energy is getting converted, this, that, so many things we are talking about. Mathematically, if I have to write, correct?
I also have one equation, which is the change in what's it called? In internal energies. And it is the
Is it the same equation?
I think it's a little different. It's yeah. So the change in internal energies are like triangle and U. So like the change in U equals to Q minus W. So it's like the
Yes.
same equation but like rearranged.
Yes. So here you were asking me, ma'am, where do we write this internal energy? This we needed to tell you, dear. Internal energy, which we talked about. What is del Q? This is heat of the system. Okay.
Yep.
Some part is lost and some comes out as work done. So see, this is heat, this is internal energy, and this is work done. So what I said, heat and work are transfer mode, and this is your internal energy.
Yeah.
Right? So if I have to talk in the form of a system, so suppose this is a system, it can be any system. So here, Swapnim, when I'm talking about systems, now I'm talking about heat engines, refrigerator, all these kinds, which we will study also. Okay, Carnot's engine, so many things are there. Okay. So what am I saying? That this system, whatever it may be, it has some internal energy. And what happens when you apply heat to it? What happens? There is a work done. That means when the temperature increases, the movement of the molecules happens inside the system. And hence, the internal energy changes. And there is a work which is done.
Yeah.
Correct? So
Yeah.
that is what we were trying to do. Now, Del Q, what I said, it is heat. But heat what? So you have to take this into consideration with too much of importance, because you will find numericals where you will see on the system, by the system, and so many things. So heat where? Heat is supplied to what? To the system. Heat is supplied to the system. I am applying to the system. By whom? By surroundings. So please don't mind with the spellings and the handwriting basically. Work done.
Okay.
Work done by whom? Work is done by whom? By the system. Where it is doing the work? On the surroundings. You should know this very nicely, because when it will be ulta, vice versa, when work is done by surroundings on the system,
I have that.
minus
It's
W.
minus. Yeah, I have work done on the surroundings is minus, and work done by the surroundings is plus.
Correct? And U, what is that? Change in internal energy, right? Change in internal energy of the system. Very important. So now I will come to your equation, which you told me, ma'am, it is rearranged. No, it has a purpose over there. Why am I writing this? Because there is a conclusion which we draw from here. And what is that conclusion? That these two are path dependent. Why? Here I told you, applied to the system by the surrounding, it will be plus. Otherwise, it will be minus Q. Correct? I said work done by the system on the surrounding plus. If it is vice versa, it will be minus. So these two are what? These are path dependent. If you go this way, it will be plus. If you go this way, it will be minus. Correct?
Yeah.
But internal energy, change in the internal energy of the system. There is no on the system, by the system. That means this is path independent. Why? Because the internal energy is a state variable on the system. State variables are what? Come on, Swapnil, what are state variables?
Pressure, volume,
Very nice.
Mass.
But these two are modes of transfer. Right?
Yeah. Okay, so heat and work.
Yes.
Yeah.
Now you understood why the equation which was written in your book, that has a particular purpose, because we are concluding something from this. And that's why general notation or general way of writing the equation is this way, actually this way. Both are correct. There's nothing wrong. It's just a rearrangement. But yes, people learn it this way, because there's some conclusion which you can draw from it.
Yeah.
Okay. Now, we will do one small example. Okay. Very small example, just to understand what we did just now. Okay. Suppose there is a system which is, whose initial states are what? P1 and V1. Okay. And this is the final state, that is P2, V2.
Yeah.
Now, change in internal energy. How it is achieved? It is not known. We don't know how it is achieved. Correct?
Yeah.
But the difference of the two paths, which is the dependent quantity, right, gives rise to the path independent quantity. Once again, now you want to know this. You want to get this. How will you get this
Yeah.
internal energy? What will you do? You will do P2 minus P1 minus V2 minus V1, right?
Okay. Yeah.
So this is your final state. This is your initial state. So what is happening over here is the difference of the two path dependent quantities. These are path dependent quantities.
Why is that one the final state and why is that one the initial state?
Okay. Initial state as in suppose you have to switch on your car. Okay. So the initial state of car will be when you are starting, the engine is cooled down. Have you seen in winters the car takes time to
I know
start.
what final and initial mean. I mean, like, why is P2 minus P1 the final state?
Yes, I will tell you.
Okay.
So that's the initial state, that the engine is not heated, it's in the cool state, right?
Yeah.
It doesn't start or whatever. So that becomes your initial state.
Yeah.
And final state is when you have drove the car maybe 20 kilometers or maybe 13 miles, 15 miles, you had a good drive and after an hour you comes. What happens when you close down, you try to touch, it is warm, it is heated up. It is not that cool. The engine is not that cool, which was in the initial state. Now it has heated up. So now these are the two things which we are saying, initial state and final state.
Yeah.
So that is what we are saying. The pressure at that time was different when it was in the initial state. It was cool, nice. But once you have had a good drive and all, finally your wheels worked, the engine got heated up, all those things happened. And then what happened? There is some final state you have reached.
Yeah.
So that is what we are trying to differentiate, minus it.
Yeah.
And that's what we are trying to say, internal energy.
Yeah, I kind of get it. But why is there a minus between the brackets?
Yeah, because both we have to minus. You can do it this way also, no? Like you can say P2, P1 minus and V2, V1 minus. This way also you can say. Minus is we are showing that there's a difference between the two states. It is actually not denoting the minus wala minus. It is denoting the difference. And when you have to calculate a difference, you will have to take, I mean, you will not add something. You will always, subtract. Suppose there were 10 chocolates and 5 are given. So you will subtract. If you will add, it will be the difference. So subtraction, the difference means the difference we are telling. The change. Change is always calculated this way. See, suppose if you say in the morning, the temperature, the sun, do you see in the weather reports, there's a sunrise time, right? And they give you some temperature that, okay, morning, say 9 a.m., the temperature was, say, 15 degrees Celsius, right? Maybe afternoon, you will find that it has become 30 degree. It's quite hot noon time, right? And maybe evening during the sunset, say sunset happens at 6 p.m. The temperature is 12 degrees. So I will say, no, I don't want this. I don't want to see this afternoon time and all. You tell me the final temperature, the state of the change. So you will take the final day's temperature, the sunset minus sunrise. So that's what we are doing here. we are also doing the same thing here. We are taking the state changes, two states, final, initial, final, initial. It can be anything. Okay, so don't worry, Swapniv, these looks, you know, a little theoretical and all, but once you see the practical approaches, you will find it more easy.
Yeah.
Once you do the numerical. Okay, so
Yeah.
2 more things I will discuss with you, and then we will start with the questions. Okay, so case 1, when the system undergoes is, I mean, the internal energy is 0. Okay, so the first thing is when your U is 0.
Yeah.
Okay, that means when U is 0, Q becomes equal to W. Correct?
Yeah.
And these kinds of process are called isothermal process. What is isothermal process? Where change in internal energy equal to 0.
0. Okay.
Number 1. All right.
Yeah.
Number 2. System is a maybe you can say there's a gas in a cylinder with you know, you can say a movable piston. For example, there's a gas and this is a piston which is movable. This is the gas and this is the piston. So this is case number 2. Okay. So what happens? The volume of the gas can be changed as we move the piston. So this piston, you know, you can move up and down. So the volume will change. Suppose the gas is less, so it will come down easily. If it is more, you will have to apply pressure on it. Right? Suppose you have to, you know, put something inside the water.
Yeah.
Do you think you just keep it and it goes? First you apply the pressure, put it inside, then it soaks the water and remain inside. Correct? So that's what it is. So that is number 2. Number 3 is when your work done is 0. That means Q equal to change in internal energy.
Yeah.
And this kind of process is called, yes, Swapnim?
Isothermal.
Isochoric.
Oh, isochoric. Okay.
Work done is 0.
Yeah.
Why? Because as the piston is moved, okay, as the piston is moved, what will I say? Work done equal to W, change in this. This means what? Change in work done means force into displacement. What is displacement? This changing of this piston is changed. It is displaced from its place and has come down. So that's what we are saying.
Yeah.
Force, you have applied a force, and as you applied force on the piston, it came down. So that's why force into displacement. Force, what do you write? Can I write it like this? Can I write force like this?
I don't know what that is.
You don't know?
No.
Seriously?
No.
Force is pressure into come on, Swapnim. You haven't heard about it.
Oh, I don't know what A is, unless it's acceleration, but I don't think it is.
It is.
Oh, it is. It is acceleration. Okay.
Yes.
Yeah.
Now you know force is this. Now what do you think is A into displacement? What do you think is this?
Acceleration times displacement.
Yes, A into displacement is V. Can I replace it with this?
I'm not sure how that works.
Okay.
It's a acceleration times displacement equals velocity.
Yes. So what you have to do is force formulas. You have to revise once again. In the terms of pressure, in the terms of velocity, just check once. You will get to know. So I can write work done like this. And if I can write work done like this, so can I now write my equation like this? Del Q equal to del U plus P into change in V. I have replaced W with PV. And how did I get this? By using this equation number 1.
Yeah. Wait, can you go back?
Yes, Swapnam.
Can you go to the next slide where you were writing about the... Yeah.
This one?
Yeah.
Okay. So Swapnev, since we started 5 minutes late, I still have 5 minutes. You want me to give you one example? I mean the numerical problem, or you want to do it in the next class?
I want a question.
Okay. Let's write the question quickly. In changing the state of a gas, adiabatically, okay, from an equilibrium state A. So state A is in which state? It's in equilibrium state, okay, to another equilibrium state B. So state B is also in equilibrium. Am I too fast? I'll repeat it once again.
Yeah.
In changing the state of a gas adiabatically from an equilibrium state A to another equilibrium state B, done?
Yeah.
An amount of work equal to 22.3 joules. 22.3 joules is done on a system. C is done on the system. Please mark it carefully. Written?
Yeah.
Full stop. If the gas is taken from state A to state B, so the gas is taken from state A to state B via process in which the net heat absorbed by the system. Be very careful. The net heat absorbed by the system is 9.35 calories. 9.35 calories. Done?